I am now going to bring in our next speaker, who is Carsten. So he's talking about our physics and more data analytics, physics of data analytics. And I'll bring him in now. So here we go, promotion to panel. And he is going to come in now and talk about our another new course that started, BSc in Physics with Data Analytics. And again, this is one where you would enter through the Physical Sciences General Entry Pathway. Hi, Carsten. And you will then take it up from second year. So I'm going to let you get on with it there now if you want to share your screen. And I'll be here to do the polls if you need me as well.
Yep. Right. Can you see the screen?
I can see the screen if you want to. Yeah, there you go. That's it. That's perfect.
All right, perfect. Yeah, so my name is Carsten Fleischer. I'm the program chair for the new Physics with Data Analytics specialty in DCU. And as with chemistry, we actually have a general entry. So if you're interested in this, the CAO offer you will find is actually called Physics with General Entry. And I'll right now, at the beginning, we'll briefly talk you through the course structures and then do a little bit of a taster lecture. The Physics General Entry is a common first-year entry for all of our physics students. So you don't have to choose necessarily straight away. You just have to choose where you want to come to DCU. And I encourage you to do so because we're part of this DCU future. So there are a lot of things we're doing differently in these courses. In terms of entrance, we have the same issue as with chemistry. We do not expect everyone to have necessarily had done physics in school. Anyone with a science, with an OH or H5 in science is welcomed. And we, again, use the first year to really kind of bring a broad introduction to the entire subject, which is then also accessible to everyone who didn't have it in school explicitly. And then it's only in your second year when you're choosing different options. And so we have the BSc in Applied Physics, Physics with Astronomy, Physics with Biomedical Sciences, and now brand new is the Physics with Data Analytics. And that's the one I will talk to you a little bit more about it today. In the first year, we really do a crash course into entirety of all the kind of physical aspects and fundamental physics which is out there. And the reason we're doing this is that physics is really something which underpins a lot of the technology we're using today. And you might have heard it in other lectures today, like when we talk about sustainability and wind energy, there was the physics in there, how you actually generate electricity out of it. If you talk about bioprocessing, they talked about measurements and counting cells and fluid lines and things like this. The technology to do this, the fundamental interaction we're doing with matter is based on physical models. And the same then in chemistry, when you're taking spectra of your molecules and you want to use them to identify them, you need to know the understandings of, if you want to build such systems, you need to know optics beyond, you need to understand how light interacts with matter. And that's exactly where physics come into play. So we're actually working in a very interdisciplinary field. As a physicist, you're not just sitting alone on a telescope anymore. The job opportunities for physicists are in all of those kind of companies, in pharmaceutical, in computer science, in engineering. And then you have the semiconductor industry with Intel in Ireland and also Applied Materials and other companies. So there's a lot of opportunity out there where the basic fundamental knowledge of all those kind of interactions and how the world really works come into play. And in a way that's really summed up with one of the modules we're running in first year, which is called Life, the Universe and Everything. So really try to get you the big picture where we sit in the world and what you can do with this. There is obviously mathematics is sort of the language we can describe the world. So there is a mathematics course, but as Emma already mentioned, it's going to be taught via this mastery-based learning where basically every student can work on their own space, with their own pace. And it is also a lot of math support there. And also for those who haven't had physics in school, we're running individual tutorials for anyone who needs catch up in the first year. So we really see the first year as one where we can really bring everyone up to speed to make a really informed decision of what they want to do afterwards. And then coming to these second year specialisms, the applied physics course is the oldest one. It's basically one since DCU has started. And that's really in terms of optics, semiconductor industry, we're really aiming for these kind of opportunities for careers there. Then the astronomy one is probably the most fundamental and kind of philosophical part of astronomy, but you might have seen James Webb telescope has been recently launched. So it's really a bit kind of learning about how the world in general works. So that's probably what you would think about physics to begin with, but it's really kind of also the engineering side and applied physics which comes into play. And we also have a dedicated degree which touches a lot more about the biomedical science. So how do we create systems to measure cells, how to kind of learn what happens there, and how we can use this information to provide the data for the chemist and for the biologist to actually do then the processing afterwards. So it's basically really the interfacing between all those technologies comes into play. And this is also part of the DCU Futures. Really, these different courses will work with each other. And some of those challenge-based learning modules, which Greg was talking about, they will actually be done jointly. So there will be a physicist next to a biologist working on these kind of problems. So this is really what we want to do with this. What's the new thing now is our spin on the data analytics part. So we really want to bring a little bit more computer science into our physics degree. This is not really a new thing. So physicists have always been on the forefront on using computer science. A lot of inventions you use, from the digital camera to your World Wide Web, like the HTTP protocol everyone is using, they have been really triggered by physical research and big research laboratories like CERN in Switzerland was the driving force behind that, because we always, if we want to understand nature, we need to measure nature, we need to kind of put this into a format we can then mathematically analyze, and that's exactly what data processing is about. So physicists have been doing data processing for the last 50 years, and so that's why that's a really natural fit in there, and we noticed a lot more of our graduates get employment in banks and insurance companies to do the data processing for them. So it's a little bit non-traditional, but we see more and more of these jobs coming along. And so this is kind of our reaction to it, because we want to create or we want to have graduates who are ready for industry and who can actually find jobs straight away. So specifically what we're doing is we're increasing a little bit the way we do programming in physics. It's not necessarily new modules, but we're using programming, for instance, to solve physical issues in other modules. So we're kind of really linking things much better together, so that you not have your isolated programming course, but you're then actually using the tools you learn there to solve problems in other modules. We have jointly with chemistry in 3rd and 4th year, we're running these special modules on machine learning, artificial intelligence, because that is kind of where the future of computing is going. It's less and less step-by-step algorithms we're implementing. There's more and more of these kind of machine learning, artificial intelligence, neural network cycles coming in. And from our perspective, it's how to use them, and that's one aspect, but it's also where are the limits? How can we trust them? How can we actually build computers which can run these different approaches on computing differently? So it's really the basis and the fundamentals behind it, which we will be looking at. And then at the same time, we also want to teach you how to really deal with large databases, how to visualize data. There's more and more of this coming along. And this is really the stuff where there's really a lot of industry demand right now. And so this is kind of the new things into it. And then Greg went a lot of this, and also Emma mentioned it already. There's a lot of more emphasis on not being just in a lecture and doing your normal exams. There's a lot more independent online learning, guided online learning. We want to do a lot more group works, hackathon. We want to bring the different disciplines together in these challenges. So there's much more interdisciplinarity. And also there's much more industry involvement. So we have like people from Accenture, from Intel, kind of helping us in running some of those challenges. And same as with all the other DCU courses in physics, we run an intro in the 3rd year where you're actually doing real life work outside of the university. And to give you a little bit of a taster how, for instance, we can see how physics, biology, data science, all kind of really meshes together if you're looking at some real problems. I actually want to give you a little bit of a taster of what we're doing in this database and data visualization module. And ask it to be a taster lecture is a bit tricky if you're actually not really basing the course on a lecture. So what I'm actually showing you is a little bit of some form of online material which you record before and which you then have access to when you're in a challenge to actually use the skills you're learning. So it's going to be one of those courses where you have a lot of online content in terms of little video clips and materials, but then we all come into DCU and do some challenges to work with the tools we want to learn there. So this is kind of a little bit of this kind of online component you would see then. So specifically, I want to give you a bit of a lecture on the physiology of human sight. So how do we actually see? What do we see? And what's color? What's contrast? And because it's the data visualization module, the really aim here is to show you why it's important to choose the right colors and the right contrast if you want to present data correctly. And so that's kind of hopefully what I can give you a glimpse today. And so let's just dive in straight away. If you would have done your first year physics, you would have learned about the fundamentals of optics. And then if you look at how an eye is designed, you have a lens and it's a single lens system. So if you've been in the physics lab, you would see then that basically means any image you will see will actually be the wrong way around on the back of your eyeball. So we're actually seeing an inverted image. And to make it worse, it's also projected on a spherical screen, so it's going to be horribly distorted. So if you ever want to build a camera, this is not the way to do it. And if we actually see what the retina, like the back of our eye, would actually see, it's going to be this really distorted image where you have lots of black areas where no light actually can reach the retina because they're kind of the neural networks going in, you have the blood vessels, so there are a lot of distortion from an optical perspective. When we look at how sharp we can see things, actually, it's only really at the point here at the back, it's called the yellow dot, I think, where you have a really high density of cells to detect light. That's the only point where you can really see sharp. In your peripheral vision, everything is going to be really, really blurry. So this is what optically actually happens at the back of the eyeball. And obviously we see the world much clearer. So what's going on here? How do we do this? And this is really a good example of what neural networks and this kind of processing of data in a non-linear way is going to do. So in our head, and we trained about this when we were toddlers and we're just learning how to see the world, you're touching things, you're kind of coordinating the signals you're getting from your eye, and you're creating the perfect image in your head. And this is kind of really the power of these neural networks if it comes to image processing. If I would take an image like this and I want to try Photoshop it to recover the original image, I would really, really struggle, because with traditional step-by-step algorithm, that's almost impossible. But we do this every day in our head, all the time. And so this is the really power of these kind of neural networks. And there's a lot of applications of machine learning actually in image processing and sorting algorithms. And Luanda touched upon this when you want to do inspection of cameras. There's a lot of applications for these kind of machine learning tools there. And the power of this concept is actually happen every day in your brain. So that's the taster for why we want to do machine learning in the long run. But for today, I actually want to touch you part of it, that our brain is actually doing a lot of kind of processing we are unaware of. And if you look at the screen now, and unfortunately, I can't guarantee that it works for everyone because it depends on your screen sizes and your resolution, you might see that this kind of torus pictured here is slightly turning around. And that's a complete illusion. So it's a perfectly still image. There's no movement whatsoever. That's not a video. If you would defocus your eyes, you would actually see it that it's a still image. And this is only happening because your brain is constantly trying to process information. And the way this image is contrasted and the choice of the color is actually leading to this kind of illusion of movement. And here's another example. So this is, again, it's a still image, but you might see a wobbling and vibration and jittery of this movement. And this is only because your brain tries to put attention to certain contrasting details, and that creates eye movement, and the sharpest area is only in the middle of it. So you kind of see this jittery, that's basically your eye moving around and not the other way around. The picture is absolutely still. So if we want to talk about perception and colors, I want to also now put in the physics side. So what is color actually? What is light? And light is what we call an electromagnetic wave. So this is basically an oscillation in vacuum where we're changing the direction of the electric field. And we can do this if we do this really, really fast, that gives us the frequency, how often we kind of turn the electric field around. And if I do this once every second, we call it 1 Hertz. And you can see that these electromagnetic oscillations are much, much faster. So if we're talking about radio waves, we're talking about like gigahertz, that's kind of your mobile networks, that's kind of this sort of frequency. If we then go to your microwave oven, we're already in 10 to the power of 11 hertz. If we're talking about infrared radiation, so heat, like when we feel the heat, this is in the terahertz region, so 10 to the 14, 10 to the 15. And visible light is only a very, very small section of this electromagnetic spectrum. And typically it is in the red area, we're talking about the distance from the peak to the peak of these waves is about 800 nanometers. So a nanometer is 10 to the minus 9 meters. And in the UV, it's a bit shorter, so it's 380 nanometer roughly. So color effectively from a physical point of view means that your light has a specific property and it has a specific wavelength, frequency, and it carries a specific energy pocket. So this is from a physical point of view. And it's really only this small fraction which we see. And so how do we perceive a light? So it's a wave packet coming in, so it's a form of energy transported through space. And the concept of this is really done in the first year, so I'm kind of paraphrasing now to just get to the point. So what we have in our eyes, we have receptors where this light packet, it's an energy packet, is now transformed into an excited electron. And an electron means we generate the electrostatic potential, or we create a voltage, and that's what our brain works on. It's just electrical pulses being sent around. So in our eye, we're converting energy from the light into electric energy. And that's the same as a solar cell would work. It's just the purpose here is to see and not to generate energy. But you can see how kind of physics plays a role in all of these processes. So when it comes now to color perception, we've seen just right now, color just means it's light with different frequency or with a different wavelength. Fundamentally, it's always the same. So the way that works is that we have very specialized cells which have what we call organic dyes in it, which only absorb light in a certain frequency range. But most of the cells we have are actually completely blind to color. So they're just designed to see as much as possible, even if it's only very, very, very little, very low amount of lights coming in. And we really mostly use them when it's dark and when it's dim. And that's why if it's really dim, you really struggle to differentiate colors, because it's actually these colorblind cells which are designed to capture as much light as possible. They're the ones who create the image. If it's bright enough and we do see colors, we have 3 different receptors, and these are now the ones which absorb light in slightly different regions of this electromagnetic range, and that's what creates our color perception. But it's not as simple as that you have, as it's depicted here. There's one cell which, I only take up red and I only take up green. That's actually not what's going to happen. When we look at the details of this, what we see is that if we have red colors light coming in, it's maybe one of those receptors, let's call it the red receptor, which takes on the electrons and injects into our brain, and that's how we detect, oh, there was light coming. If I switch now to yellow light, it's actually the red ones and the green ones which are, it's not that suddenly the red one stops working, it still sees the yellow light as well. It's actually not that precisely tuned to one specific energy. And it's really the difference between red and yellow is only that in one case it's one type of cell firing, while in the other case, it's two different type of cells. So we're doing a lot of processing in our brain to interpret this as color. And oops, this is not supposed to be, okay. Here at the background, apologies that this one isn't just supposed to be only coming in later, is now what we call a spectrum. So it tells us at what frequencies and what colors an individual receptor actually absorbs the light. And we have 3 of them, which are normally called short, medium, and long for the type of wavelength they're absorbing. And the short one is really very specific only in the blue. The medium one, and I'm deliberately not calling it green because the peak of it is sort of in the green range, so that would be still okay to call it a green receptor. But the one of the long wavelengths, the peak actually there is in the yellow, so it actually absorbs yellow light much better than red light. The way why we perceive, for instance, red as red is not that it's just this one is firing, it's basically this one in the red is firing a lot more than the green one, while if we are at the yellow or kind of mid-green, both of them are firing at the same time. So it's the activation of these different, and this activation pattern, which in our head creates the color. And that creates a problem because everyone is different. And persons have actually different percentages of these type of cells in their eyes. And so the color I see might be completely different to the color you see, because you might have a completely different ratio of these cells in your brain. And that makes it really important when we're designing graphs, because we need to be aware of those differences, and we need to be aware of how our brain processes color. And I think I'm running a little bit late, so I'm not going to talk too much about this, but I want to come to the next point, which is that color and also the contrast, how we see color, so what's bright and what's dark, decides of how our brain puts up our attention. And as I've shown at the very beginning with these optical illusions, our eyes are drawn to certain types of contrast, and that they're drawn to and creates eye movement, that eye movement creates the perception of movement there. But when we're presenting data, when we're kind of making graphs, we want to make sure that we're not working against the way our brain works. So we need to know what kind of thing works and what doesn't work. And for this, I just have a little test here. So I made 2 colored text lens here, text A, text B, text C. And if Colette could run the poll, the first one.
Yes, indeed. Stop sharing this
The
one.
question is, which of them can you read best?
Now, where is your poll? Oh yeah, question 1. Which is this the one that which text is easiest to read in the slide?
So there are 3 different texts. There, text A, text B, text B. And I just want to kind of see like which one of them you think, or for you personally, you can read best. As I just mentioned, perception is subjective, so there's no wrong or right here. It's really just kind of which one can you see best.
Okay.
All right.
So we've had a few people. Well, they're still answering. Hold on a second. Give them another few seconds.
I hope there's still actually people around. We know
there is. Well, no,
we're really overrunning. So
you're getting the answers here anyway. Even if they're here for the other for the next talk, you're still getting answers. So I'm going to stop it here now.
All right.
And share results.
So now the interesting results. Okay. Surprise, surprise. It doesn't come as a surprise to me because text A has the highest contrast. And so it's the one, so 9 out of 10 say text A, 1 likes the red one, and the green one everyone found was really, really hard to read. And that's exactly the point. Our eyes are really, really kind of perceptive in the green, and white is basically just a little bit more blue cones. So there's very different in the activation of these neurons between the green and the whitish, and that's why it provides very, very little contrast, even though that I'm actually using the same intensities of the light. And the blue one, we have the fewest blue cells, so that gives us the best contrast between the white and the text, and we can actually put numbers there. And so, for instance, text A, if we and down here is a link. If you ever want to check that for yourself, if you're making graphs, it tells you that this text here had a contrast of 1 to 1/8, while the green one is really kind of very, very poor contrast. And that's why we actually make a rule that if you're making graph, if you're making text, you should have at least a contrast of 1 to 4 to make things easily readable. And the smaller you make the number, the larger your contrast should be. And it's really not just something that we want this from you. It's actually something which naturally helps to process the information we want to display. And that's exactly what we want to do with data visualization. We want to make it easy to process the data. And so I have another question prepared for that, and I have to prime you for this one, because when I click my mouse button, there will be 3 letters appearing on the screen, A, B, or C. And I really just want you to ask you, check yourself, which letter do you see first? Is it going to be the A, the B, or the C? So I give you 2 seconds to prepare yourself. 1, 2, go. All right, so now the poll. Which one did you see first? So maybe, are there answers coming in?
Oh, there are, yes. Yeah, absolutely.
I don't see that.
Okay, give them another. Okay, we have lots of people answering. Okay, so I'll end it and share results.
All right, so you see here now, it's actually not that clear cut anymore. So there's a bit more, I don't know if people see the results. So A was still the most popular choice, but then B and C had kind of slightly even numbers. I think this is now, we have a small sample size here. If we have a bit larger crowd, we'd actually see that probably the majority would say A, but C would not be that far away from it, because they actually do have more or less the same contrast. And it's probably now just, I probably should have put them on a straight line rather than up and down, because we read from the top. So psychology also plays a role there. So A and C have actually the same contrast, but it definitely is you're much drawn close, you're much earlier drawn to these kind of high contrast, because the activation pattern in the back of the retina and then also in your brain is much easier to process, because it's a much larger difference in signals. And that's exactly why we've drawn to high contrast areas and why that focuses our eyes a little bit. And that now brings me kind of to the last part I want to, so this is just the summary for this. When you're creating text, when you're making slides, be careful that you use at least a contrast of 1 to 4. If we have black and white, that's always the highest contrast, but it's also the most boring slide. So it is perfectly fine to use color, but you have to make sure that you still kind of have a good enough contrast for it to be readable. There are then other aspects in the course in terms of, for instance, the distinction between red and green. A lot of people are what we call colorblind. They don't, or a lot, I think it's only 4% of the population. They have difficulty in distinguishing red and green. So that's something we should technically avoid in graphs, which everyone should see. And then likewise, we've just seen poor contrast can be problematic. And if you have, like, for instance, here's a really bad example where I have a really high contrast grid line. So the first thing you will see in this graph is actually the fence and the grid lines, rather than the data points I want to show. So we have to be careful when we're designing our graphs to use something which doesn't draw our attention away from the information we want to convey. So we have to be careful in not just relying on color as a distinguisher, simply because color can be different for different people. We want to really increase the contrast. If we have small text like down here with the numbers, with the months, you really want to have even better contrast there. And you also want to kind of explain within the graph what it's actually all about, because it says here Dublin monthly average temperature, but why are there 2? So what is this actually showing me? So it really is an example of something how not to do it. And then if I click one slide further, this is a much better way to do it. So first of all, we don't have anything which distracts from the graph. We have an explanation that the blues is the air temperature and the orange ones are the sea temperature. It's in the same graph, it's in the same area. I can focus onto it, I can see it actually quite easily. We use a different shape, not just color. So it also makes it easier to process for someone who perceives color a little bit differently than us. and also the text is a bit more contrasty and a bit larger to see. And so this is my crash course in trying to kind of give you some idea about some of the aspects what we want to do new and differently in this physics with data analytics one. But first and foremost, and that's probably the same as Emma answered already with the chemistry one, it is still a physics degree. So this example is not kind of what the course is really only all about. It's just one example of an additional module we're creating to prepare people a lot more than we would have normally done it for these kind of jobs in the data visualization and data handling kind of industry. And with this, I actually want to finish, and I hope I can see you all in DCU, and there will be open days where we can have chat about this as well. And you see, we have a lot of color in the rooms as well.
Well done. A lot of color there. Absolutely. Come and visit us at the open day on the 2nd of April. I'm sure Carsten will be there to talk to you about all things physics at DCU. So that was really interesting, of course, as well. And I want to thank you very much for your presentation today, Carsten. So yeah, well done. And the polls are great. And they worked very well. It's great to see everything. I'm learning so much today myself. So I don't think we have any questions coming in the chat, so we can let you go if you want.
All right, time to get some food.
Time to get some food. We time to get some food. All right, thanks a lot. I'll talk to you soon. Thank you. Bye-bye.
Bye-bye.
Bye-bye.